Everybody. Welcome to today's webinar, Concrete Design in RISA. My name is Debbie Penko, and today we'll be discussing all the concrete features here that we've got in RISA-3D, RISAFloor, and RISAFoundation. We've added a lot of new features into the programs over the last several years, and specifically, today we'll be focusing on our upcoming software release. So this will be version 13 for RISA-3D, version 9 for RISAFloor, and RISAFoundation will be version 7. These are all beta, so they're not available to you yet, but they will be soon. So I wanted to show you some of the new features, but I will also be showing features that we've added in the last couple years. So Concrete has been in the program for a long time, but we've spent a lot of time developing some great tools, and today we'll get to show these off a little bit. So kind of walking through some of the big one that I want to talk about is concrete design rules. We've enhanced the concrete design rules in the program and actually in all three programs. And the design rules, if you're not familiar with using concrete in RISA-3D, for example, we use design rules to help define how the program is going to design the reinforcement. So in steel, we talk a lot about sizing things. We size up the members and size different wood. We do that as well. But in concrete, a lot of times more the size is defined maybe by the architect or the layout. But what we're doing for design is the reinforcement. So you can size the shape up and down, but more often you're interested in sizing that reinforcement. So adding a graphical interface to this reinforcement design makes it a little easier for a lot of different ways. So we see that on the right side here we have a graphical input that's going right on top of our existing member design rules, and that helps us to see a beam or a column type and visualize what we're inputting there. And I'll show you that here shortly in the program. But also that we added an ability to do explicit rebar. So this helps you with as-built situations. So you can quickly enter in, you know how many reinforcement bars are in that. You can enter it right in, and then it will actually check those bars instead of saying a suggested amount of bars or sizes. So it's a check or an analysis versus a design of the reinforcement. And we made that a lot easier to do. You could always do that, but hopefully this graphical interface makes this a little bit easier. And we have this in all three programs. So I'm going to focus today on RISA-3D with these design rules, but you'll see them in RISAFoundation and in RISAFloor. So jumping right in, I'm going to go using, let's see here, I'm going to go into my desktop and open up RISA-3D, the background. Here we go. So in RISA-3D, I just have an example model to work with here that is this is actually a parking garage structure, just one bay or one frame of that. And if we look at it here a little bit, what this is using actually is section sets. So section sets, if I show you here on the right side, it says column, girder, or beam. And those section sets are grouping these members together. So we've got some beams in red, some columns in blue, and some girders in green. And the section sets help us to develop a model in such a way that we only need to make changes in that one place in the section set location. And then we can later on here, let's jump into my section set for concrete. So we can see all of my section sets are listed here. We can make changes to the material, the design rule, which is what we're going to be talking about. But any of these changes can be made quickly here, and then it applies to the entire structure. So this is a great example of why we'd want to use section sets, but let's open up. What we're also going to be using here is our member design rules. So as I mentioned, you can change the sizing of your shape for your suggested shapes in RISA. You can lay out your sizing, but we're going to open up our graphical interface of that. And the way I did that, I just clicked on that little red arrow, and it opens up a graphical interface. Now, this is just our typical design rule. It comes in kind of blank, not much information. And we can change that in order to have the program suggest better shapes for us. So for concrete, I'm going to actually leave this as it is for the size. Since I'm not going to get a size, I'd like to go with the rebar. So for rebar, I can see here I have an optimized rebar or explicit rebar. So first one I'm going to lay out is going to be a column. So I'm going to change the design label to be column. And I'm going to change the member type to say column here, so we see a picture. And for the column, you can do the optimization where the program will size it anywhere between a number 5 bar and a number 10 bar. But I'm going to actually jump to the explicit rebar because this is a really cool feature for columns. You can click on just total vertical bars and you say, hey, I want to evenly distribute these bars. I can say a number, so 4, 8, whatever I need to do there. So I will start out with those number of bars here. I'm going to just pick, let's see here, maybe pick 8 bars. So if I pick 8 bars out of or maybe 12 bars, we can say choose number 6 bars and see if that works. So you go ahead and say this. We lay out the edge distance from the center line. We lay out the flexural bar size. We can keep the shear bar size as number 4s. All that's laid out. And if you're ever in doubt of what these numbers are, you'll see there's a little information bar. So whenever you click in there, it should tell you a little bit more information about what you're doing inside of that box. So I'm going to say OK, and I'll come over here to the concrete rebar, and you'll notice that the actual rebar layout is listed right here as well. So it's easily, you can change it and enter it directly into the spreadsheet. But what we're going to do here is push enter and create a new one here using our graphical interface for the beams. So if I just switch over to a beam type, I'm going to call this a beam. And the same thing I'm going to use as explicit for the beam. So for the beam, I can lay out what kind of bars I want to use. And let's say this is going to be number 6s. We'll say that we're going to use maybe 2 bars on the top and the bottom. Let's actually say 3, maybe a little bit bigger. And then we'll go ahead and say shear bars. We've got number 4s. Again, that's probably fine with a 12-inch spacing for our stirrups. So I can say OK. And I'm going to do one more for the girder. The girder, I'm going to let it optimize. But let's just jump in and see what that happens here. So for optimizing, we give it the range. And I'm going to just narrow down that range a little bit. Maybe we'll say number 6 bars all the way up to number 10s. And the cover information is listed here. So I'm going to say OK. And now I have all of those labels already created for my reinforcement. The last step in order to use these is to come over to the section sets and just assign them directly as the girder and the beam. And now my reinforcement layouts are already in place. So I can double check that. Of course, it's already in the section set, but I could double click on any of these columns, for example, go over to the design tab, and it says here use design rule. So it's telling the program here it's going to be using that design rule. So it kind of explains it for us. If I'm going to solve this model, when I go into my load combination spreadsheet, I can see that I have my dead loads and my live loads and earthquake loads are actually what's being run in this model. And let's just take a quick look just so we understand what this model is. So we have some downward distributed loads for dead and live, and I have some earthquake loads that are actually entering right into those frames. So the best idea for concrete design when you're in RISA-3D is to run the batch with the envelope. So if you click on the solve button, you'll see it's here, batch solution with the envelope listed there. So I'm going to say solve that. And the program is going to run through all of those load combinations, and it's going to batch them together. And we'll actually see that the detail report is going to be giving us some information on the envelope instead of just a single combination. So here we get a warning log, and first of all, it just tells me here my custom rebar layout doesn't meet my area of steel that was per the global parameters. So let's just take a quick look at the global parameters. If I open the global parameters, there's a concrete tab. And in here, I see that I have a minimum percentage of steel for columns as 1%. So that means I'm not meeting that with my layout. And that was because we did it explicit for our concrete columns, and so I'm not meeting this. It's just going to warn me. It will still give me results. If I wanted to move forward with results on those columns, I could just click on that detail report, and I could find out a lot more information. What was nice is it gives me that warning again, so I'm not going to forget that. But it goes through all of the calculations there for me, because that is going to be a warning here. It's not going to stop the design, or an analysis in this case, but it does tell me, hey, you didn't meet the code minimums. So quickly and easily to do that, I can just go back into my member design rules, and I can change this column instead of being what we currently have. Let's see. So in our column report, we have evenly vertical bars. We're using 12 bars. Let's switch that up to 16 and maybe jump that up to number 7 bars. And go ahead and solve this again. So you could run that. Now that warning goes away, and I now see that I have no warning in the warning log. But then when I check a column again, I can see that that is now missing from that. So I can see all the information here in the detail report for this column. What you'll notice when you do explicit in RISA, you'll see that I'm actually running here, it gives me like a little line telling me what is the code, what's listed there as a capacity there. So we're doing good on this one here. Let me double check. So you've got, and this is an envelope as I mentioned too. So envelope makes it that I'm seeing both a positive and a negative moment in this one because we're actually pushing on it in multiple directions. So we're seeing an envelope solution. It's kind of different than what you'll see for any other material. So you've got ability to see all that information right there. When you see the code check information, this is also based on an envelope, so it's running through. Maybe the bending check is not happening exactly at the same place as the shear check. Depends on what's happening in your model, where these are happening, so where the spikes are happening for you. So this is all going to be based on the envelope. As I scroll down below that, I see my column interaction diagram. So I'm going to see here my capacity line with some little squares here, or excuse me, plus signs indicating where we are on that. So we're pretty low on this. This is pretty low to code check here, so it wasn't really that stressed out. And really what you'll notice is what filled this reinforcement was the area steel requirement. So it's kind of an interesting layout. We probably might be able to figure out a better, maybe it's a lot in there, but maybe we could size the bars up. Depends on what the cost of your construction is, if you're going to use less bars and bigger size, or if the steel costs more, things like that. So I have detail report for a lot of information for the beams and the girders. But I also have some information here on the results toolbar. So concrete reinforcing is also listed out for us directly based on all the results. It gives us a nice tally. And you'll see here you've got the beam bending and beam shear. So none of our beams are requiring us to have shear bars. If we go back to our columns here bending, it'll tell us for the columns. And so for explicit, it's not going to give us any of those information for the columns there. But it would be for the beam since we let the program design that. So I can click on a beam and refer to the beam report as well. So again, you get the envelope diagram for that beam. It gives us some information here, and then I can scroll below that and I can see all the information for the reinforcement for the number 6 bars, 3 number 6 bars on the top and the bottom, and I scroll below and see more information there too. So you're going to control all that information based on the rebar, based on these member design rules. Let me jump back here and talk about my next feature here. So the next piece I want to talk about here is RISAFloor ES. In RISAFloor, we added concrete tools, but based on a new floor type called a concrete floor slab. RISAFloor ES is going to be a built-in add-on into RISAFloor that allows you to have access to these concrete floor slab types. And we'll see that inside of that floor type, all concrete design is going to be done in there. So two-way slab design and punching shear allows us to design an FEA slab mesh on top of a floor, which is brand new, and it's going to be designing the reinforcement. I'm going to show you that in just a second. You'll get the punching shear. You'll get all the checks involved for area steel, all the information that you're going to need for your two-way slab. You also can do your one-way slabs with beams in RISAFloor, in the concrete floor slab, and also the T&L beams. All these can be done right inside of this concrete floor slab that's going to be enabled with RISAFloor ES. So what this adds is a lot of a different ability here. I'm going to jump right into RISAFloor. So let's go ahead and jump into RISAFloor. I'm going to shut down RISA-3D for a sec since we are done with that. And if we go to RISAFloor. In this model I've built, it's kind of a good example. It has a lot of different a lot of different shapes to it. So one of the things I like to show off, let's see, this is a two-way model here. And in RISAFloor ES, I like to talk a little bit about the shape of the model. So this is what you'll notice right away is that the entire shape of this model is irregular. There's no beams really at all in this. What we're looking at in this is a slab with columns. So you can just see if I just toggle it, it's a slab, kind of actually looks like a shark, but it's of any shape kind of a slab. And this is what a real life type of structure, and I want to make sure that you guys understand that you can do any kind of shape with RISAFloor ES. It has no restrictions on framing, so a lot in RISAFloor with steel buildings or wood, A lot of times you're talking about framing with beams and doing frame. You have to worry that there's a closed circuit and it's very constrained by the beams, which is how you construct those types of materials. But in concrete, it's a little less constructed like that. You can do a lot of different things. One of the reasons why we would design in concrete when I was in practice was because of things like this bump out over here. Might be a difficult thing to do in a steel building, but in a concrete building, it's pretty easy to lay out that. So you have a lot of different freedom in your shapes here in concrete. And in RISAFloor ES, we see that in this model. So the way this model it looks, I just did a representative of one floor so we could just understand that. And if we just look at it in full model view, it's just one floor with some walls and some columns. And I'm going to jump back to that single floor. And the way you would work out for a two-way slab, you can see that you do a slab definition. So we have a semi-rigid and a rigid diaphragm. We'll talk about the semi-rigid diaphragm here shortly, but that's a brand new feature here. But I want to talk about that you define all your information here, the thickness, the type of concrete you're going to be doing, all that, and you can draw it in this slab edge. And I did that prior to this webinar. But I want to show you also is the next piece is for design. So the design rules that are for the slab are based on the slab design rules, which are listed on the data entry toolbar. And if we go over to the general tab here, we see it just gives us some maximum bending checks and cover for top and bottom. And then the slab information. So you tell the program specifically what kind of bars you want to place. So top bars, bottom bars. I have number 6s defined everywhere. And the program will decide what spacing is needed. So we have a maximum and a minimum spacing listed here for both the top and the bottom. And then I also can define the deflection. So deflection is going to be a pretty important piece for a slab design. This is all can be seen if we open up our rules here. We actually have a graphical interface for this, just like we did over in RISA-3D. So you see here that you can define all this information directly on the graphics. So we can say number 6s and the spacing and then the deflection. So I'm going to say OK. And now in order to get the reinforcement design, what you do is you lay out support lines. So I actually laid out support lines in one direction already, in the north-south direction. So when you look at this model, you'll see I have a support line that is going from each support point. And it's going to, so I have it from column to column or column to wall. I drew it over top of this wall here, and we'll come back to this when we talk about the results. A lot of people ask about how the walls interact with the support lines, and so we'll review this in a second when we get back to results. But what I want to do is lay out the ones in the other direction. So I'm going to go ahead and just view them in the east-west direction and show you how I laid those out. So you just click on the support line on the left side, and you choose east to west in the east to west direction. And I can tell the program here I just want this design strip width to be automatic. So all we're doing is clicking and finding the support directions. So I click from east to west, and east to west and north to south are general. Okay, so they're just, since we're talking about a two-way slab, they're general ideas of going in that perpendicular directions. They don't have to be exactly north-south to east-west, but they do. You want two opposing directions, and so we've kind of gone with that convention of saying east-west, north-south. So I'm going to say apply, and then it's going to give me a pencil tool, and all I have to do is just connect the dots. Okay, so I'm going to connect the locations here. I'll just click on a support point and then just drag my mouse to the next one. You can see it's pretty easy to do. You just, the mouse is actually going to be detecting all those column lines, so it's not a very difficult thing. I'm going to click on any of these here. And so when the geometry goes a little different, as you'll notice, and probably, talking to any architect, right, they don't want to do a straight rectangular building for us. That would be too easy and boring probably to look at. But what that means is we're just getting a little bit more creative in how we're laying these out. So we have to sort of have the ability to click on things along the way. So, as we talk about this as east to west, this is really just a general east to west. It's kind of, I'm clicking on this direction mostly. Now, what you'll notice is I stopped a little short on some of these, and I can continue those if I want to do that. So when I click on support line, I had the options here to make some modifications. I'm going to actually modify here these edges. So I can extend the support line. I can just tell the program, hey, I want this actually to extend out a little bit. So I click on that support line there. Let's see here if I can grab it. Let me grab this one. I'm not quite able to grab them right now. Let's see. So what I'll do actually is I'll just draw on top of that one. So support lines do have spans to them, but you can continue to draw them anywhere you want. So you can see here it just continues off of that back span. Not a big deal. So I'll grab this one here and I'll just continue it over here. There we go. And I'll do the same thing up here. I'm going to continue it to that point right there. Okay, so once you have them all laid out, then you can generate the strips. So by generating the strips, you can say here, I'm going to go ahead and look at these design strips. You can see the program automatically flushed out those support lines as a design strip. And so it goes to its neighboring design support line and cuts it back about halfway. So sometimes when things get the directions changed like this, we can see that they kind of they couldn't find a neighboring strip. And that's not a big deal. What you can do is just make modifications to that. So it's really easy to grab that one and drag it back. So I'm going to click on this one here. I'm going to grab the redraw edges. I can actually edge align. Let me edge align that one. So edge align this edge here with that edge there. Pretty easy. This one here, let's see, these are probably easier to drag, but maybe edge align this one to that one. What you'll notice as soon as you make a modification, I'm going to redraw some of these edges here. As soon as you make a modification, it turns purple. And that's just kind of a good way for us to guide what we're doing so that we know, hey, the program actually generated that, or maybe you made a modification to that. It just kind of actually, for me, helps me work around the structure and understand which ones I've been working on and which ones need to be cleaned up and stuff like that. So none of these, just if they're kind of big, they overlap a little bit. That won't really hurt you anyway. Maybe it will double dip on top of that, which means that you'll get reinforcement in overlapping. Not a big problem. Some of these you'll notice kind of happen anyway. You get little gaps here and then you overlap on that side. So by the time all this is said and done, you've kind of worked through it. If you really wanted to, you could straighten that out and just have it extend cantilevered. That would be okay. You can draw cantilevers around. You don't need to connect support line to support points. You could actually cantilever, as you'll see I did on the left side. But it kind of makes a little bit more sense. So once you have them all laid out, I'm going to run the analysis, and it's now running through and actually designing the reinforcement. Internally, the program is submeshing this into plates. So all of the slab is going into submesh into small FEA plate mesh, and the program is then going to assign the forces throughout these, all the forces in the plates, and then after all the forces have been determined, then later on it goes ahead and does the design on top of that. So let's just see here for a second. You can see the forces and how they're flowing here. We have a diagram. It shows you out of plane moment directly on your slab. So you see here the moment just shown here. You can see the shear, and this is showing us the moment and the shear is in the two-way. So we're looking at the slabs in both directions. The two-way strips here as well. So you can see all of that laid out for you. We can also see contours. So if I'm going to look at some of the contours on this slab, I'm going to go to the slabs, and we can see here the slab contour. I'm going to contour it. Let's see. Let's show MX. Let's see. Maybe look at some here. I'm not seeing. Oh, sorry. Contours. There we go. So I see the contours listed on here, and we have a nice plot plan here. Shows us exactly what we're looking for the contours. So this is just a really nice way to see what's happening in your slab. You don't really need all this information for the design since it's already going to be done inside of those design strips. But it does help you confirm how your slab is moving there. So I'm going to actually get back to the wireframe for a second. And what you'll see is you have a design strip on top of this. We said the design strips are done. But the other thing is also we can see is we have a column strip. So inside of that design strip, it's broken into column strips, mid strip left, and mid strip right. So the way that's determined is how you drew the support line. So you'll see that you've got a column strip in the middle. And the idea behind that is really, if you check out the code, it's really the idea is that you're going to have most of your forces running through that column strip, and the mid strip left and mid strip right are just going to catch some of the other smaller forces. So if we look at our detail reports and information, we'll see 3 different terms: the column strip, mid-strip left, mid-strip right, and then we'll also see total. So sometimes we're just going to see the entire strip and how it's behaving. And then we can kind of drill down into the reinforcement. The reinforcement design is based on each different region. So let's take a look at our detail report for a second. I'm going to click on, let's go, actually here, I'm going to jump to the all, and we'll click on this. Let's see. I'm having a little time grabbing this. I wonder if my projector's causing that here. Let me look at my results, and we can actually go ahead and look at our design strip results this way. So if we go into our design strips here, I'm going to open up there we go. So if I look at design strips here, I can get into, we have a spreadsheet of design strip results, and then you can also open a detail report right from there. And so I see here that in my detail report, it gives me an information based on the total. So I see the entire design strip, how it's behaving. So it gives me the shear and the moment, and then it gives me the forces inside of that shear and moment diagram. So the span by span, it gives me the information, and the deflections by that for the entire strip. And so internally, the program is making cuts inside of that, design cuts, and then it's doing a summation of that for the entire strip here. But really, we don't do reinforcement for the entire strip. We do it for piece by piece, as I mentioned. Inside the column strip, we do one. We do a different design for the mid strips. So if I go to the column strip, and that's on the top there, I'll see very similar information, except now I get my reinforcement listed. So I have a nice diagram describing what the reinforcement is. It gives me all of the information based on the reinforcement and the development length. And then I see below that, and this is all the supports that are attached to it. Below that, I get to see all the analysis information, just like I saw in that total report. And then I go into the code checks, and now this is listing out what the code check was for the top and the bottom, and the reinforcement listed here too. Now, this reinforcement, again, is based on an envelope of cuts. So we did a ton of cuts in there, and I'm just going to actually show you that for a second here. I'm going to go back to just looking at maybe the design strips here, and we can add these cuts. So you see inside of there, you have these little cuts across each design strip. And that cut can be determining, that's going to be determining what we're going to be, the analysis inside of there, what the forces are, and then what the design of the reinforcement is. So when we look at that cut, let's take a look here. When we look at the design strip, it tells us, hey, that SL2, S1, X1, that was the governing cut that caused this reinforcement. Maybe when you start to look at ones that have got a little space, like maybe here we see 12 inches on center. So we're seeing SL2, which is the support line 2, span 1, cut 50. That's what governed for this one, and that's why we have that design. So in order to investigate that further, you'd go ahead and you'd click on the cut. So SL2, S1, X50. That's what we want to take a look at. So SL1, so we said span 2, X50. Okay, so when I jump over to X50, which is the last cut, this cut is what governed to give us that reinforcement design. So we look at this a little farther, and we see here that this is the column strip. It's giving us all the code, the top bending, the governing moment here, and for the top and the bottom. And then what it really breaks down even farther is how that got determined. So the area steel required is based on the analysis, the 4/3 limit here, and then the minimum flexure. So you have 3 different types of checks that are happening. We actually had 0 bottom in this here, so this one didn't govern for bottom at all. But we do see here that we've got a listing here. So this 4/3 check here is what's going to be governing for the reinforcement. So that's what's the reinforcement. If you kind of scroll along, you'll see these kind of bounce about, and that green number shows us what governs. So it's a really helpful tool because we're seeing here what's actually governing for us. And then if we kind of look at, let's go back to our strip. So you'll see you've got column strip, mid-strip right, mid-strip left. You have a lot of information listed in that. And the idea with those mid-strips is hopefully that there's not a lot of positive moment, which means maybe you get to skip out from putting a lot of that top reinforcement in there. You only need it when you're getting into that positive. So this one you get to see we did not have to do any reinforcement over the top. Now, you can see on the screen, I'm using these tools here, you can see the reinforcement. Let's look at all the total bars in the north-south direction. So you can zoom in a little bit and see we're displaying the reinforcement on the screen based on this design strip. So for this entire design strip here at the middle of my screen, I have 19 number 6 bars, and they're spaced at 18 inches on center. And that's for the entire span here. And then whenever you have a top bar required, we have the top T listed there in parentheses. So on this portion, there's no positive moment, which means no top bars required. On this side here, we are looking for a little bit of top bars. Now, the other thing I get a question a lot is about that wall. How do we do the design strip over that wall? So on one side, I actually put the design strip over that wall, and on this side, I did not. And it's really up to you. You pretty much don't need that design strip. Let's see if I can open that one up there. But you can take a look at what's happening. So this is span 2. That's span 2 right here. And what span 2 is telling me is that there's really not a lot happening in span 2. This is the column strip that's coming right over that wall. And you'll see this is the total strip. And there's very, very little happening in there comparatively. But if we go to the column strip, we see even much less happening in that middle strip there. In that span 2, there's like no moment practically. For a lot of it, maybe just put a little bit of top bars in there and you'd actually satisfy all you needed right in that area there. But what you could also have done is just dragged the neighboring design strip over to it like I did on this one. So you can stretch that over and maybe capture what you need in this mid-strip right, and that would actually capture versus drawing one over top. What happens is there's just really not a lot of forces happening over that wall. The wall is really stiff, and so it's sort of sucking all of that right in, and you're not seeing it in the slab as much. So in order to do that, you could just kind of capture what's happening in the slab around it and not actually draw one right on top. So that kind of makes a little bit more sense. But it's up to you. You can draw it directly on top and see the forces that you see right in there as well. So you can sort of change between, I'm just looking at north-south here for a second, but we can see east-west total bars, all going in the east-west direction. The program is checking spans, it's checking punching shear. All of the results here are listed here. So you have strip deflections. It gives us some information if we didn't satisfy the strip. So you see this deflection is 225, which is going to be in red. That's a little low for here, 172. So we are seeing some failures in this dead load plus live load ratios, and that might be something you'd want to maybe thicken up the slab slightly or things like that. You also have all of your, I showed you earlier here, your reinforcement and your cuts. If you put any cuts in there, so you've got all that. You can see your slab forces. This is just kind of a tally and really kind of just a quick review of what's happening. I would probably go into more of the design strips and versus looking at just a tally, but this does give you kind of maximums and minimums, which is really nice. And if you're looking at seeing how much force is going in there. And then the punching shear. So we're doing a punching shear check. Looks like we have one punching shear failure. So we'd have to investigate that punching shear failure right there. And the program, you can maybe put a cap on there. Right now this is just the slab failing, and so it's an edge condition. It's telling us here that slit covering is actually going to be having a problem, and so we'd have to maybe thicken that up a little bit in that region with a shear cap. So you have an ability to take a look through a lot of different things for that design. Now I'm going to jump back here for a second. I want to talk about that semi-rigid diaphragms. So we've had rigid diaphragms in the program. We added flexible diaphragms when we were working with wood in RISAFloor, but now in RISAFloor ES, semi-rigid diaphragms have been added. And it's really important for a slab design that you can have semi-rigid diaphragms for when you're getting over to RISA-3D. So you can do it in either way. It's really easy to flip back and forth. You can see I have semi-rigid listed here, and you can just toggle it. I'll show you that here in a second. There's some kind of interesting modeling tips to talk about. So for a rigid diaphragm, we typically just model the lateral elements. So we do the shear walls, maybe. If we're talking about steel, we do moment frames and brace frames and shear walls. Whatever is just the lateral element, that's what we take over to RISA-3D. And the rigid diaphragm carries the loads throughout that and distributes it directly to those elements. Now, when we're talking about semi-rigid diaphragms, we're going to actually model all the columns and walls as lateral because we need to hold up that slab. The slab is actually going to be in place over in RISA-3D, so we're going to call everything to be lateral for the vertical elements, and then we can let them carry them through. So maybe we do a pin base if we don't want them to carry much moment there, but we actually do want to make sure that it stands up when we apply the vertical loads over in RISA-3D. And so let me show you guys an example of that. But I also like to talk about how the loads get applied. Semi-rigid diaphragms aren't quite just as easy as a rigid diaphragm where you get to put the load as a point load directly into the model. In RISA floor, when we move over to RISA-3D, the program does some automated loading for you. But for semi-rigid, you actually, it's more complex. You have to drop it into the diaphragm now, more as a different type of loading. So for wind, we talk about applying that distributed load into the diaphragm. So we calculate still one value, and then we take it and distribute it along the entire diaphragm. And the way we do that is we apply it to a windward and a leeward force there. So we calculate the windward force and the leeward force, and we apply it to each face. And you'll see here we have created a WL plus X and a WL minus X. Those are two different categories. One is going to be pointing in the direction of X, and the other one is pointing negative X direction. And you'll see those categories are defined here in the basic load cases spreadsheet. I'm going to show you guys this example in real life here a second. But I also want to show you here that the Z does the exact same thing. So it applies it right into the diaphragm, and that diaphragm is submeshed in RISA-3D, so I'm showing the mesh in this, and it's applying directly to the diaphragm on each side. Now this is wind, and wind is applying it directly like that. Now seismic's a little bit different. So seismic actually gets distributed as an ELX and an ELZ. There's no windward-leeward idea there, so we don't need to do the directional. But what we are doing here is we're putting a surface load directly in there. So the surface load is going to be counting both the weight of the slab and the dyne load. The dyne load is coming, what we call a dynamic load or dynamic mass that's coming out of RISA floor, defined as anything superimposed above and beyond the dead loads. So, or above and beyond, the slab weight. So that's your dynamic load or your dynamic mass. And then we times that by your CS or your seismic response coefficient. So that's going to be what we call here as a surface load, and you see there's a green outline that's going around. But the other piece you have to account for is the weight of the columns or the walls. So you'll see that there's point loads there, and those weight of the columns or walls are being accounted for in those with times the CS or the seismic response coefficient. And so you'll see those little blue point loads that are happening all throughout the structure. And that CS value you'll see right listed in your seismic loads parameters. So you can see directly on the input, you'll see when you draw that in, you'll see that CS, so you can verify that number. The other thing is you've got the ability here to we added some internal force summation tools. So in RISA-3D, the program isn't going to design your rebar, but you can use this tool quick and easy to find your forces and design the reinforcement for yourself. So this is going to give you, we always had internal force summation tool, but it's been a thing that goes across the entire plane. And that wouldn't help us too much because we want to actually find more of a localized what's happening in the slab. So we've added this tool that will find the plate forces right directly inside of RISA-3D. You just draw from point to point inside of a slab. You can say from point to point, I'm going to locally grab each point in that slab. And you can see in my picture here, I just click on a couple points, and I get the forces directly in there. It works for slabs and walls. We added two tools. So as a benefit, since it's a very similar tool, we got a wall tool that will help you just do the same exact thing in walls. And it's going to give you those loads there. The other thing is really important to note is based on your displayed results. So that's just like if you've ever used the internal force summation tool. It's based on what you're looking at on the screen. So something to remind yourself of. So let me jump in and take a look. So let's see here. Let's go back to my RISA floor. And I just use my kind of a simplified model because I just want to make sure we understand the concepts. So let's go ahead and jump into what we call here my internal force summation tool model. And it's just a copy of that tool. I wanted to make sure that we understood how these loads are being applied. You can do it in a very complex model, but then we don't get to see all the basics. So Here we've got in here, we're looking at, we're just the same exact thing, and we have a slab definition, and this is a semi-rigid diaphragm. So the only change there, we just flip that switch and we go to an 8-inch semi-rigid diaphragm. And I didn't note that here, but I just want to earlier, I want to make sure that you guys understand that currently you are doing a submesh inside of RISAFloor as well. So you have an FEA submesh. It's all happening right under the scene. It's just that we're not display. You can turn it on in your plot options. It's not displayed at all times. It's a little complex to see, but you can see that it is happening there for you. So once you've run the model here in RISAFloor, you can take it over to RISA-3D. I click on RISA-3D, and I see in here that I've got the ability to put some loads in here. So my wind loads, I can change the category, maybe C, and I push calculate loads. And below that, I get to see all the information for this that I just input. The ASU 710 calculates all of the coefficients. And I then scroll below that, and I see that I get a windward and a leeward force. So those are really the numbers that I really care about here. So the pressure in the windward and the leeward force. Those are the directions that I care about. I'm going to say OK. And then if I'm in here for the seismic, I'm going to see ASU 7. I'll put an R value in. I'll leave it as 3. And so I'm going to go ahead and put some values in here. So maybe 0.16. I get 0.27 and 0.1, and then I say calculate the loads, and I then get to see all the information here. So as I mentioned, that CS is listed right here, 0.09, and then I see that we've got the calculated force in the X and the Z direction. A really good tool to always remind people. When I used to use RISAFloor, it was my go-to was to check the weight. So if the weight of your structure is not something that that makes sense, like if this 838 kips for my structure does not make sense to me based on my simple hand calc I can do just to check the loads, then the forces aren't going to be very accurate. So a quick back of the envelope check is to check that number. And I didn't mention, let me just bounce really quickly back to the floor spreadsheet. I did want to just point out here, in the floor spreadsheet, you have the area load definitions. And when I mentioned that the dyne load here is listed, this is the dynamic mass or the dynamic load here. And that's what we're using. So we're using the weight of the slab and the dyne load. And that's what's going to be calculated to account for the seismic. And I'm going to pump over here. Here we go. And when I jump right over into RISA-3D, you see that there does an outline of the slab for me. So automatically that slab is already in place. It's not submeshed just yet. Actually, that submesh that we did over in RISAFloor gets recalculated over in RISA-3D because maybe you'll have some additional loads or elements in here, so it's recalculated for you. And then at this point, we can see here, so we've got a lot of those different loads here I showed you. We've got in the spreadsheets now, when you're looking at the point load spreadsheet, you can click on there and you'll see there's a diaphragm point loads, and they're all in gray, but it gives you the ability to see them. So this is all our magnitudes, and then you can also see our distributed loads in the diaphragm. You just go to the diaphragm tab. It's a new tab, and you can see all the loads that are being applied into the diaphragm, and then the surface loads that are applied there. So you're getting a variety of loads in our spreadsheets. Kind of easier to see for me when I just go into the display and see it right on the screen. So if I look at this, I can see exactly those values. So you're applying them directly into the columns. You have a surface load around the exterior, and then you can see all the ELX, ELZ, all listed directly in the different directions for the seismic. And then as I mentioned here, so you've got the wind loads as well. So in the basic load cases spreadsheet, you have those new semi-rigid wind loads, which you can then see as well. And we look at that and as graphically because I think that's much easier to see graphically. And you just see how we get the wind loads applied to the structure in the windward and the leeward directions. So when you're doing load combinations now that you have a fancy generator, fancy seismic loads here, you actually want to make sure that you apply. So I'm going to go to United States in the strength here, and you'll see that it generates semi-rigid diaphragm loads. So it's important to use this button here in order to create these different load combinations because they're going to be using the new seismic load combinations that we created for you for wind. Seismic's actually already is pretty easy and laid out for you since we already had those, but the wind is going to be the new one that's got the different types of loading, the WL plus X and the WL minus X. So I'm going to solve a batch solution. Let's See how it will run through, and it's going to divide all of everything. It's submeshing, so it takes just a second to run through and solve this, but it's going through all the combinations. It's submeshing that, and then it's going to apply all the forces that we've just applied to the structure. With these results, we're going to be able to use our new internal force summation tool to play around with to see what the forces are. Okay, so I'm going to close that down a little bit. And what we've got in here, let's take a quick look. If we look at our diaphragm, I'm going to keep it turned on here, and I'm going to jump over to my diaphragm tab, and I can show the mesh of my diaphragm. So I'm seeing that it's all submeshed into plates. But probably what's easier to understand maybe is our contours. So you can play around and look at the contours as you're developing that. So you've got a lot of different load combinations to look through. So you can see that as the display, you just toggle the below there to see which different load combinations are causing. Maybe what you might want to do is find a high deflection. That might be something that would be an indicator of the worst case for us, and see how the loads are being distributed through the forces, through the actual diaphragm. What you also can do here, I'm going to actually go back to wireframe for a second. And what we can see here, so we have a deflected shape. The deflected shape also works right off of that toggle. So you would also want to maybe go ahead and toggle through and find the deflected shape, and you'll see how that is. So not a lot's moving, but you can kind of see, and you might want to amplify this a little bit further so you can really understand how things are going in the model. So you just go ahead and amplify that magnification. You also, so let's go ahead and use our tools. So the internal force summation tool on the left side allows you to check the wall and the slab. And first thing I'm going to do is the slab. Once I click on that button, it activates the mesh, so it allows me to grab on that mesh. And maybe I want to do like a strip, a couple different cuts or strips. So what I might do is be able to cut, and you see I'll just click 2 points on the slab, and it will find the forces for the slab for me. So you've got forces F2. So it depends on what we're looking at here, what type of forces we're interested in. Maybe we go in the other direction, and this becomes maybe the direction. And the way that we're calculating these is, again, a brand new global axis, just like you would see when you use the internal force summation tool, except it's set to the actual slab. So you don't have to, you'll notice I'm breaking the rule of an internal force summation tool. I'm looking at it in isometric view. However, this tool allows us to do that, just clicking point to point. So it's just determining it based on this new axis here. So this is the definition of this axis. You'll see is from A to B is the one axis, so F1 direction. F2 is upward, and then F3 here is going to be normal, so then the opposite direction of the clicking. Perpendicular to the click. So you'll see maybe F2 seems to be pretty high for us, which is going to be forces in the vertical direction off the slab for this, what we're looking at currently. So you can apply different types of loads to this structure and see how that's going to be, how this internal force summation tool really helps you to design that reinforcement. Now, the walls can also be used. If you click on the wall, you can then find all the forces inside of a wall. And that's also really helpful because you can then click point to point, maybe over several walls. You can use this wall tool over several walls. They all have to be in the same plane, but that can be done over several walls. So internal force summation tool really helps you to understand the forces in that, but contours are also a really good method to understand that too. So I'm going to jump back here for a sec, and let's talk about RISAFoundation for a bit. So RISAFoundation also got some new tools. RISAFoundation, we can take our model directly from RISAFloor or from RISA-3D, either one, and we can design now new wall strip footings. So walls were added a while back into RISAFloor and RISA-3D design, and now we can actually just go ahead and do the wall strip footings right inside of the program in RISAFoundation. There's a couple different ways to do that. It's doing the strip footing gravity only, and that means that it's going to look like a whole, almost like a retaining wall. We're going to see the whole wall together, the strip footing with the wall element on it, and we're going to get a report based on that entire wall strip footing. So it's a really helpful way, although it's going to be just accounting for the vertical loads, not any lateral loads. If you do want to account for the lateral loads, we have a way to do that with the custom, and that custom report there is going to allow you to build a generator. It's actually going to build a slab and a design strip on top of that with a stem wall on top of it. So it's kind of just three different parts of it, and we'll see that in a second here. I'm going to jump into the same model. So I'm going to go right back to the same exact model we were working on. And let's take this over to RISAFoundation. So just using our director button, I'm going to take that model. It's going to take all of the loads. Now, if you're not familiar with RISAFoundation, it took all of the loads from RISA-3D and based on its category, so live load, dead load, all of the different types, earthquake load, all of that. Actually we use ELX, so we'll find it down here, ELX. And so all of these loads are going to be right from RISA-3D. So it's a really great tool because it's embedded. RISAFloor can also be just used right as a standalone, so you don't need to do that if you don't want to. But it did do a lot of the work for us, so that's really helpful. So I'm going to go ahead and take a look here with the new tools we added. So you can always, we have things like footings and slabs, and we'll put those in as well. But the new tools we added here are going to be the stem walls. Strip footings that allow us to do these little stem walls in there. So if I do the strip footing, I'm going to open this up for a sec here. And what I see is I have the ability to apply any type of wall in here. It's going to give me the thickness. This is going to give me the wall height, the heel height. So you can go the toe and heel. Right now we have 3 and 4 feet. The soil height. It gives us the soil gamma there, the thickness of that footing. And then really probably what's more, once you lay out all your geometry, we want the rebar. That's what we're looking for. So for our rebar, maybe we can set this to be number 6 bars, like on the top and the bottom, on both faces. You can switch from each face to single layer if you wanted to. The program is just going to give you you're going to tell the cover information. I'm going to switch everything to the number 6 bars. In my practice, I've always kind of thought, hey, use the same bars unless you have a good reason not to. Otherwise, kind of confusing in the field about what you're doing there. But maybe you want to do some lighter ones for the longitudinal. I'll use some number 6 bars anyway. So everything is number 6 bars. And then the program is going to find the spacing. So it's minimum and maximum, and it determines what we need in our model. So I'm going to say OK for all of that information. And then I'm going to go ahead and go to my strip footing. Let me lay this out. I'm going to lay out the first one here. Say apply, and I can just click on a bunch of nodes here. I can click beyond the nodes, but I can click on the nodes themselves, and it will lay out this strip footing. So I've got a couple different in here. What I also might do is use my custom one, just so we see the difference. So I'm going to go ahead and use the custom one or the lateral one and see that. And what you'll see is just a generator. It's just going to allow us to create these 3 different parts: stem wall, slab, and design strip. So this just goes ahead and says, hey, what would you like to use for your slab? And it's 4,000, let's say 4,000 normal weight. We can do a couple different kinds of design strips on top, break it into segments. I'm actually going to just do 1. And then very similarly, we tell the program the thickness of the wall, and then the slab thickness and the different dimensions here. So that's okay. We'll leave all that okay. And we're going to draw this on top of here. Now, very similarly, this goes just from point to point, and it flushes out and gives you the strip footing there. Now, if I look in isometric view, just see a slight difference, and I want to show that. So this is going to be really just a slab. So it's a slab with a footing on top of it, or a stem wall on top of it. And you can adjust that. You can redraw that slab. So you can actually do kind of any shape you wanted with this. Now, this one is going to be more of a set element. So this type of element gives us a report on it, which is really helpful. And it allows us to see some information on just that stem wall and that strip footing there too. So the other piece I can do is I can lay out some footings. The footings I can put in this model here, I can just highlight a bunch of these and drop in some footings, and I'll put in the slab as well. So you can also draw a slab directly into the program in RISAFoundation, and I'm going to just do point to point to create my slab, and then I forgot that last point. That last point is what determines your end. There we go. And I'm going to expand the slab just slightly so that it covers a little bit. Usually don't drop a point right to the corner. So I will kind of open that up a little bit. And just like in RISAFloor ES, you use design strips to do a horizontal and a vertical design strip. Now, We don't do support lines in RISAFoundation. You just go ahead and do a total design strip. You draw it whatever shape you want it. I'm going to actually go horizontal on this direction, just a massive one. You might want to do more of a localized design strip where you cover like a different direction for, you maybe do 3 in here in different directions. But I just do a large one for the whole mat. Maybe they'll all be designed kind of averaged together. So, and then you can see in RISAFoundation, you can solve this. Let's solve that. And I'm going to run the solution, and it will go through and it'll check both of these combinations for us. And we'll see the results for this. So for a slab, it's pretty easy. It gives us, let's look at this for a sec here. It'll give us the reinforcement. Now that reinforcement is based on our reinforcement rules. It's kind of spaced here at 18 inches on center for the top and the bottom, which gives me a feeling that it's probably running off the area steel minimums. We probably hit there. So you might want to change the bottom bars from number 8s instead of number 8s, maybe number 6s or number 7s, something like that. And that data, if you go to your data entry toolbar, all of the information here is going to be listed on our, let's go to our reinforcement rules. So if we go to our design rules, you'll see on the mat slab, you've got, right now we're laying out bottom bars as number 8s. So maybe we should change that to be number 6s because it looks like maybe we'll get better spacing. If we solve it again, we can change that and it will just rerun the solution for us and maybe we'll get better reinforcement there. And yeah, so we now start to see a little bit better spacing. Maybe 18 was something you wanted so it would work out, but probably a little bit better. And here we see this is also basically what I mentioned is a slab. So we're going to get the same information on this strip footing as just a slab. And so when we look at this here, we can see this. We can look at it and we just see the reinforcement design based on the slab right here. So again, just like we saw on top, it gives us the number 6s for this direction. Internally, we're cutting cuts right through there, just like we saw in RISAFloor ES. And so those cuts are listed directly like this here, just like in RISAFloor ES. Now, if you do the other type of the gravity only type, you can see if you click on it, it gives us a picture a little bit different, more like a retaining wall. It gives us the reinforcement of the wall with the footing portion. It gives us a loading diagram, kind of breaks it down, which is really nice for that's going to be undergrade, so we have some overburden. And then I scroll down here and it gives me a detail report type that's going to break out the wall design with the reinforcement, as well as if you scroll down, it gives you the envelope results for the wall. Then it breaks out the footing design, and it tells us what the forces are for that footing. It's going to check the sliding and the soil bearing check. So it's just slightly different in the way that the results are presented for each type. If you want the overburden, if you want the sliding and information for this one, you could find that in the results toolbar here. So you just go, in your results toolbar, you can find all of your information on that slab. So if we go to, let's see, point reaction, so soil pressures, you've got all of that listed, and then you can find all the slab soil pressures listed right there, and all that, and then you can also find your strip cut results listed right inside of here, and then the safety factors gives us the sliding factors here, and then the overturning, so per each slab. So it's a little slightly different. You also can see your wall footing results. So if we go back to our wall footing, we just, again, see that in more of a spreadsheet type of format. And then footings is as well. So footings, if you're not familiar with RISAFoundation here, this is just very similar actually in layout of the detail report where you get to see the pedestal and then the footing, and then it breaks it down into the different types of checks that we do, as well as the overturning check. So we've got a lot of new things here in RISAFoundation, as well as we showed RISAFloor ES and RISA-3D. And